to the main event today. Computer vision, a new approach to data science and geology. I want to introduce our speaker, David Thul. He's also the CEO of GeoLumina. David is a geologist and a geochemist with broad global exploration and production background. He has worked 50 basins in 15 countries as an explorationist and raised and deployed more than 100 million in private equity capital. He is an EMP technology patent holder and is always looking to improve how the industry does business. So with that, I would go ahead and have David take control here. And while he's getting set up, I just want to remind everyone that we like to get questions throughout the talk. So there is a Q&A button on the bottom. If you go ahead and you press that button as David gives his talk, you can submit a question. And then once we get to the Q&A at the very end, which I'll facilitate with David's support, we can get to that in an orderly fashion. So that's enough for me. Why you guys came here. David, the floor is yours. Thank you so much for taking the time to do this.
Thanks, Brian. Yeah, I appreciate it. Thanks everyone for joining me tonight. I hope you all have a good dinner in front of you. I can't see you on camera, so I'll just assume you're eating excellent food, just like you would in person at one of these things. Tonight's talk is a little bit maybe different than what HTS is used to from a geoscience talk in general, but also from a data science perspective. So like Brian said, it's about image-based AI and classification. And in this case, we're going to use porosity and permeability cross-plots. So I put this talk together with Callie Blevins, who is an ace computer programmer and my colleague in all things geoscience. And, we're pretty happy with how it turned out. It was really a test case. We wanted to see what exactly could we do. Okay, so I like to tell stories rather than just give like a straight up technical talk. And there are like 3 arcs in this story. The first one is, where are we in artificial intelligence and machine learning in geology today? There are lots of different approaches to this topic, and I think it's worth a quick survey since going through everyone's backgrounds, there are a couple data scientists, but a lot of consulting geologists and some private equity people and some general explorationists. So I want to address kind of where we are and how the landscape looks. And then, we're really adapting a technology from another field, computer vision. And so I want to talk about basically what the approach is in leveraging that. And then finally, kind of the most slide-rich portion, I'm going to talk about the actual process and the results. And I think it'll be a pretty interesting series of 3 stories for you guys. So, AI is really impacting oil and gas in a huge way. Everything from how we monitor equipment out at the well site to how we predict well forecasts to how we commission fields and automate all kinds of remote operations. Kind of underpinning it all is machine learning, and really it's time series based machine learning. So it's taking data every second, every minute, every hour, and looking for anomalies, and then helping people make decisions based on that. It might alert someone that a pump is going to break down, or it might connect people that need to meet on a some sort of a route that they're doing to alter production in the field. And even with all of this happening, like those fields are very well developed, they're very built out. There's multiple companies competing in that arena and making a lot of different solutions. But if you ask me, geoscience and exploration in particular have really been left behind in a lot of ways. And the reason for this is complex. It's a little bit institutional, right? Because everyone thinks that they're smarter than a computer, and I agree. We all are smarter than computers, and no one wants to lose their job to a artificial intelligence, and I agree with that. Like we don't see AI and ML as taking geologists' jobs. I don't think that's very reasonable, and it's not very likely. And really, underpinning all of this is what AI and ML are good at and what it's not good at. So machine learning in general is really powerful when you have evenly spaced data. It could be over time or over an area spatially, something like that. So seismic cubes are a really great venue for machine learning because the seismic grid, as far as the computer understands it, is evenly spaced and easily interpretable and can be dealt with in very clear ways. It's most at use, AI and ML, in geoscience related to geophysical data. And that's good, but I'm a geoscientist. I'm not a geophysics guy. I'm not a seismic interpreter by nature. So having AI and ML in seismic data doesn't help me. It doesn't ease my load. It doesn't change what I do every day. And so that leaves me out and leaves a lot of us out, because I guess people have this common misconception that geologists do seismic interpretation. And while that's a part of it, it's not really all of it, is it? So I always like to show this slide as a motivation of where machine learning and geoscience doesn't work very well. One place is in actual well log data. Like it's pretty good at going from one well log to the next door well log, but it's not great at interpreting space in between because of the irregular spacing of the grid. I think everyone can understand that, where seismic fits in because there's an even number of points between here and here. If we're working with subsurface data from logs and cores, et cetera, that spacing is a challenge. There's also really irregular data types that might be core descriptions and biostratigraphy, and in a lot of cases, it's just not digital. So there's this huge burden of digitizing, and digitizing is a little bit problematic just because it doesn't really create enterprise value immediately. Like in the long run, it helps, but immediately it does not. And then there's these visual recognition tasks that geologists are always doing, right? Like it takes us a fraction of a second to understand that all of this is bioturbated sandstone and all of this is laminated sandstone and this is laminated mudstone and sandstone and this is a bioturbated sandy mudstone. Like that, it's instantaneous. And I think we all know how fast that happens. It takes the human brain just milliseconds to recognize what it looks at. And the same goes for things like bin section data. Sure, you can have point counts or you can have aggregates and numerical data, but the reality is most of this stuff lives as pictures in our world and not as numerical data as such. So the progress has not been very solid in geoscience because the data are just less suitable. They're not structured in the same way that a computer looks at information. So, there's this interesting data resolution problem, and that data scientists, if you go and talk to Google or Microsoft, they're just like, yeah, we can do data science and oil and gas, sure. And yes, you can, but there's this data resolution problem that feeds in. So I always like to ground truth this, because big data in oil and gas and big data in the world of actual data are totally different scales. So if I look at like cell phone GPS pings in the city of Austin, where I live, over the course of an hour, it's like 4.6 billion. Like, okay, that's a lot of GPS pings, and that's just assuming it's refreshing every second. But if I go to like a common onshore US basin and there's 50,000 wells that average 6,000 feet deep, it's only like 900 million data points. So like we're already off by an order of magnitude. And the way you can automate insights from that is totally different. So like if none of you guys know this cartoon, it's XKCD, and this illustrates the point that I constantly run into almost all the time. Like as a geologist and as someone that works in the programming space as well, you always run into this, and they're like, yes, we'll solve this with algorithms. And then you come back later and they're like, wow, this is hard and there's no solution yet. And yeah, it turns out exploration is hard. Making better decisions is difficult. And you really can only do it by addressing the world as a portfolio. So, if you think about the exploration process as making good decisions about as many different things simultaneously so that you have more positive outcomes, that's really what exploration and production is all about. Because every time I put a hole in the ground, I don't actually know what I'm going to hit, right? Like you have some inkling, you have some knowledge, you have some regional understanding, but I don't think anybody ever hits exactly what they expect whenever they drill a well. It's the reason we still drill dry holes, and not only do we drill dry holes, but we drill dry holes because of things like there was no reservoir there at all, or there was no oil in the reservoir at all, or I thought it was a closure, but it wasn't a closure at all. Like we don't just make minor mistakes. We make big fundamental understanding problems because of the ambiguity of the subsurface. And that's okay. Like that's kind of an intractable problem. So let's talk about things that are tractable, things that we can fix. So there's another great plot, again, from XKCD about over the course of 5 years, how often you do a task and how much time you shave off. And, the funny thing about this image is like, I think geologists generally live in the yellow box, but really we probably live a lot of our lives in this orange box, or even like down here where they haven't even calculated the amount of time saved. And the reason for that is interesting, and it's because we're actually doing a lot of different things at once, right? We're recognizing patterns, we're collecting data, we're loading data into other software, we're doing all of these tasks, and I like to say that we spend a lot of our workday on task time and not a lot of our workday on thinking time. And so the goal of AI and geoscience in my world is to change that load of the geologist. It's to change the cognitive load. It's to make it so we can spend our time thinking instead of our time doing. And I also run across an interesting thing every day, and it's that the challenge of like saving time as a geologist isn't automatically seen as creating value in a company. And like, for example, if I save time drilling a well, the engineers have no doubt that saved money and value and time and created more value at the company. But that's not always the case, right? You and I all know that drilling faster might lead to poorer results, or it might lead to suboptimal results. And geoscientists kind of have the opposite conundrum, which is if we save time, people don't know that that's a better thing for the company because they're not thinking about it that way. Like, we're not saving time to save time. We're saving time to make better decisions. We're almost always time crunched. We're almost always working on an evaluation that has a deadline, or we're working on 4 projects simultaneously, but we only have 2 projects worth of people. And so all of these things actually need to be tackled in geoscientific AI and machine learning. And man, that's a huge problem. It's not a problem, it's a challenge. So, okay, so that's the like intro. That's the like, where are we in the world of geoscience? Okay, so let's motivate my approach here. So I wrote in the abstract, and I'm going to say here again tonight, that geologists are really subject matter experts at pattern recognition. Like we're like the best pattern recognition engine on the planet. And we get this way through training, right? Like there's that old saying that whichever geologist sees the most rocks is the winner, or that sees the most rocks is the best. And there's truth to that, right? Because experience matters, and also, applicable experience matters, and also failures and mistake matters. And really what we do is we abstract concepts from one location to another, right? We look at patterns. And so if you don't believe me that geologists look at a lot of patterns, like I've made a slide full of patterns that we recognize. Like, we might look at a Buckles plot to find water saturation and productivity. And like this is a graphical tool, right? Like you can, yes, you calculate all the numbers, but really the goal of calculating the numbers and placing them on the graph is to evaluate them visually so that you can make quick, solid decisions. We have the same thing in the porosity permeability space, which we'll be dealing with tonight, which is, we're really plotting these data because the trends have meaning. And the interesting thing about graphs is that, well, you and I can visually understand what the pattern is. It's actually programmatically very tough to calculate and understand the relationships. So sure, if I have a plot that is just one set of data, I can fit a line through it relatively simply. Computers are good at that. But if I have all of this data on the plot, the computer is not great at knowing which of these are trends and relate to one another. So that's actually a visual recognition task, right? Like we're going in here and we're saying these data are all related. Let's fit a line through them. The same is true for picket plots. They're kind of doing the same thing, but also geochemistry data, right? We're looking at what's the trace of the chromatogram and what does that mean compared to our experience or other samples that are available. Like it's just visual pattern recognition. We do the same thing with various drawdown plots in engineering and reservoir engineering. Like so many of these things are just, we're looking for a visual relationship. And so AI and machine learning can be a complement to this task if we deploy it correctly, right? If we deploy a numerical solution, it's actually going to be really challenging to get the correct one. But if we deploy a vision-based solution, it becomes actually much simpler to get the correct answer. So, okay, this might be a little bit ambiguous because maybe none of you work in computer vision arena of data science. So I always give this simple example. This is a version of computer vision that everyone understands, which is the self-driving car, right? So the way the self-driving car works is the machine learning model is trained to understand what does a car look like. Not only what does a car look like, but what does a car look like from multiple different angles? And also, what does a person look like? And what does a traffic light look like? And by identifying those features within images, the computer program can make decisions. It can take action. It can do some sort of thing that's programmatically involved. And so there's kind of two steps, right? There's the recognition task, like the computer vision needs to recognize what an item is. And then there needs to be some rule about what it does when it finds the item. The rule is don't run into the person, stop at the red light, go when the light is green. All of these things are input, which is the picture from the camera, and output, which is the action from the rules. And so, these are the kind of same powers that we're working with in our approach to geoscience. This is my favorite slide I've ever created because it's the simplest way to convince everyone of the approach, right? So what do? We have a corpus, a body of input data. In our case, data are images. They're not numbers. They're not spreadsheets. I mean, they are numbers, but we'll get to that in a second. But they're not spreadsheets of data. They're not porosity permeability data. They're pictures of plots in this case. So, in this case, this is our rock classifier. And we've put in images of things that are mostly rocks. There's Kid Rock, and there's Chris Rock, and there's The Rock. But there's also like the rock imposters. And so what we have to do is train a model to recognize these classified items. And then we test that model to make sure we get some correct percentage of guessing. Because what we want to do is to be able to see The Rock and know that it's The Rock, and Chris Rock and know that it's Chris Rock, and also that it's Kid Rock. So that's kind of the process I'm going to walk you through today that we did with porosity and permeability plots. So again, like the approach here is image-based AI. So if I can say it as simply as possible, it's that we set out to train machine learning models to identify geology as like visual pattern interpretation. This is the same way a geoscientist works. It's fast when the computer does it. It can address biases, but you can also build biases into it, right? If you only train on certain types of data, and in a way, actually, like positive results can be bias if we train in a certain way. And also, it's quantifiable, right? So we can quantify the error, and that's actually what the machine learning model for this project did. Is it tells us the certainty that we're seeing a pattern within a graph. Okay, so like this is the pipeline workflow. We gather data. In this case, images are the data set. I can't emphasize that enough. Like I don't care about everything else. All I'm doing is working with images. And those images could be scraped off your hard drive, or they could be pulled from the internet, or we can make them synthetically, which is actually what we've done in this workflow, which is we wanted to find a certain pattern. So we created a bunch of training data that identified different patterns of porosity and permeability relationships, and we trained a model. So, first you get the images and then you data condition. In our case, we didn't have to do much of this step because we created all of the images from pseudo data, from synthetic data that we invented. And then you kind of refine the model by trying it and testing it and seeing how it works. And so this is actually like an iterative pair of steps: model training, model testing. You get a result, it's either satisfactory to you or it's not, and so you go back and you retrain the model, and eventually you iterate towards something that works to your satisfaction. And what that threshold is depends on the task. And then down the line, there's something too. You can deploy a model, right? So you maybe make a user interface so other people can use it, or you just use it in your workflow from the command line, whatever that is. And so model deployment is actually the functional use of the trained and tested model. So we wanted to make a test case, right? Like what exactly can we do and what can't we do with machine learning and image-based AI, computer vision. So we just set out to try something that I do quite a bit in my own prospecting work, like the porosity permeability crossplot. I work a lot of Rocky Mountain plays. I buy a lot of old fields, and what I want to do is identify undrilled pay or pay behind pipe or just missed opportunity. And so, there's certain trends that I like to find in these porosity and permeability plots. So, the way we frame this problem is, let's just say we have some concept of a porosity and permeability relationship. And we just pulled this from the literature. This is actually on like Gulf Coast wells. It doesn't matter where it's from, right? As long as you know what you want to find, you can make a synthetic data set. So we said, okay, cool. Like this is a good conceptual model. So what we want to be able to do is find other images of porosity and permeability plots that have these relationships in them. It's a little bit artificial, but it's a task that probably every geologist on this call has done. They've gone through well reports, or they've gone through data, some sort of literature report, or they've made the cross plots themselves and then had to visually look through them in order to identify the trend and the ones that fall on it. So our lives are full of this. Geologists, not only are we image recognition machines, but we're also image creation machines. Like the hallmark of a good geologist is maybe one that makes a bunch of images every week as part of their interpretation load. So, I'm going to interweave in here a little bit of how, like, the tools I used and how we did it, in some code snippets and a lot of technical flavor. you don't really have to get caught up on that, and I'm not going to belabor it. I'm just trying to explain the process and how we went about it. So, okay, our first step is we have this subject image, and this image contains things we want to look for. So our first thing we have to do is we have to digitize some data, because we don't have data and we can't fit a line through data. So we use this little applet called Plot Digitizer. It's actually Python code. And you can download it from GitHub and use it yourself on your own machine if you're so inclined. If you're not inclined, you can actually just Google Plot Digitizer, and you can use this thing for free and download the data sets that you create. So it just lets you go in and click on points in order to pick out the data that you want. And you can save it as a data set. You can save each different curve as a data set. It's pretty straightforward. It gets even easier if you happen to have a color image, because you can change the parameters of color detection and basically how big the pixels are that are getting detected, the cluster, and how far apart from your desired value they are. So the you can really get automated and pretty high zoot. So instead of having to go in and click all of these little dots, the computer found them for me. So that's super fast, right? If I'm lucky enough to have a color image, I can get to my data creation step really fast. And like I said, the goal is, right, that we want to create a data set. Well, we want to create a relationship that allows us to abstract it and create a bunch of different data sets that create a number of images that help us train a machine learning model to identify the thing we're looking for. And you're probably saying, like, my God, Dave, like, how much time did you put into doing this to not save any time? And the answer is, it takes quite a bit of work on the first one, but all of the rest of them are almost free, because once the code is written, all you have to do is change some variables, and it works as well for Buckles plots and Hingels plots and this plot and that plot and a Van Crevelen diagram and any damn plot you can come up with. So this actually turns out to be really powerful, because the first time is slow, but every time after that is very fast. So the funny thing is, we're using a free output from Plot Digitizer, and it's not very good. It gives us a weird data structure where there's this index at the top, and then there's a 0 row, which is another indexed row, and then there's X and Y data values. So this is the X coordinate on the cross plot. This is the Y coordinate on the cross plot. And this is a coarse and very coarse trend line, right? So we're looking on this coarse and very coarse grained. That's these guys here. And you end up with not really super functional data. So okay, now we've got to change how the data look. And we're just going to write some code. And all it does is take the data set and transform it so that we instead have X, Y, and then the name of the data set. And we're going to drop the ones that don't have values, because you can see, like, not everything is digitized, and there are a bunch of nuances to it. But eventually we get to a pretty straightforward data set that represents all of the values in that cross plot. Okay, now we've got something we can start cooking with, because we can stick these values into another piece of code, and we can use that code to fit a line to it. So, okay, let's look in this case at the fine-grained trend line, or fine-grained data. And I always like to plot it in two spaces. One is log linear, just like the normal porosity-permeability plot, and one is just a linear space. So you can kind of intuit, like, how complicated this data is. Like, in a perfect world, right, this should be a straight line in that log linear space, but there's almost always a hinge point that's related to lightly compacted versus heavily compacted, and water escape and clay transformation and cement overgrowth and all of the other things that happen in the subsurface. So we want to look at these two things. And so what do we do then? Let's just fit a baseline curve attempt. So we've created this exponential function. There's nothing complicated about it. It's just fitting the exponential to the data in the graph. And we're just plotting it over here. All this block of code does is plot it. It's pretty approachable. And this is almost always a garbage plot. That's the technical term for it in data science, which is, fitting one line through this data does not work. And that's cool. We understand geologically why it doesn't work. So what do we do? Well, let's go ahead and split the data into groups. So we've got this like undercompacted world, this kind of compaction transition zone, and the more compacted, normally compacted stuff that we see in the deep subsurface. So great, this is awesome. I can just fit some piecewise functions in here. If anybody remembers way back to middle school mathematics, before we learned about differentiation and higher order functions and all the critical things that you might do, like we're just going to fit multiple functions to suit our needs. And I didn't even fit 3 functions here. I only fit 2. I fit the deepest data and the shallowest data. And you know what? Like that's pretty good. That does a pretty good prediction job. So what I want to do now is I want to basically make a bunch of synthetic data between this X point and this X point and this X point and this X point. And that'll create me a bunch of pseudo Y values, right? So I'm just going to use the function of the line, some bounding boxes in order to make artificial data, synthetic data, however you want to think of it. Don't stress about this. Like, this will not be the least inaccurate part of the model. Like, you don't need brain damage over this thing. And I'll show you why in a little bit. So, we create some code to make a random function. And so, we're just going from the bounds and we're selecting a number of points, and we want to create a random sample, and it's going to generate Y values. And this is what that looks like. This is what it looks like when we use code to create a bunch of random data. And now you're probably looking at this going, awesome, Dave. Like, how is this useful to me at all? We've got no noise. We've got perfectly symmetrical data sets. Like, this doesn't look like the original plot, not one bit. And I'd say you're absolutely right. But what we can do is we can add error. And, we probably want to add error on the scale of some percentage of the Y value. And so we can go in here and basically multiply in a random value that is, say, between 1 and 10% positive and negative of the value that we created. Like we can come up with any sort of realistic value. In this case, we generated a random number around 0 with a standard deviation of 0.25. And that gives random values of approximately 10%. So, this is like pepper to taste or salt to taste, right? So if your core repository or core lab is much better than 10% error on porosity measurements for a certain permeability, or vice versa, you can tighten that up. Or if it's historical data and it's really crappy, you can blow those numbers much bigger. And by doing that, you create randomly distributed error around the plot of the line. And that's awesome, right? Because now we can account for all types of things: sampling error, testing error, geologic error, misdigitization. It doesn't matter, right? Like, the absolute accuracy of these 2 lines do not matter as much as them representing a cloud of data around the thing that we're looking for. Because it's not absolute, right? The machine learning model is basically going to learn where is stuff on the page that we are interested in. And then it's going to look for stuff on the page in the region in which we're interested in it. So, you can, like I said earlier, you can abstract these functions, right? So it doesn't matter that in this case, it was for porosity permeability of, these Gulf Coast sandstones. We could have used anything. We could use shales. We could use things from other countries. It doesn't matter. We can just refit the data when we come up with a new use case. So we don't have to reduplicate or duplicate any of this effort the next time. And so this is what we create. This is just a picture from my drive of all of the cross plots that represent this medium to coarse relationship. And you can see like they've all got error. They all look a little bit different, but they're all highlighting a region of interest that we want the computer to find. So what we do is we go in and we create sets for each trend we want to look for. And we train the model to identify those trends. And what the computer model actually knows is just the color values. So 0 is black and 255 is pure white. And you can see that this is just a matrix of color values. So the computer's not doing anything totally cool. It's just treating vision as though it were numerical values, which is actually pretty awesome. And so, okay, so now we've got a set of images like this for every different thing that we're looking for. And we throw them into a machine learning model. We might use, a lot of times we'll use a neural network because those kind of see the same way human beings see. So it's difficult to explain, but they identify features and feature prominence and feature location within the workspace. And by abstracting that and putting filtering layers on, you basically end up with a machine learning model that understands how to find things in place. So what we do is we train, and it iterates and it learns, and it says, okay, this group looks like this, and the other group looks like this. And there are a lot of things you can do to train the model. I know there's at least one data scientist in here, so I'm going to hit on this just really briefly. But in this case, we're not doing anything crazy. We're not training a neural network from scratch. We don't need 100,000 images to make it function. We used like 1,000 images per category. And we also didn't go in and fine tune hyperparameters and lock different layers. Like we didn't do any of that. And you're going to go, well, Dave, why not? Isn't that essential? And I'm going to say, not in this case, because differentiating locations of things on graphs is a pretty simple task. Like it's not difficult to do. It's not like identifying different types of birds, which is something we have done because Callie is a certified bird nerd. So she made a cool app that looks at what birds are and identifies their species, which blows my mind. And that's how we ended up down this path. I thought, like, damn, isn't that just what geologists do? They look at complex images and identify important things. And so what we found is that when we go through a series of images, so actual images, things from literature and core reports, the model will identify the exact trend that we're looking for correctly, like 84% of the time. So that means that it will find the exact right thing 84% of the time, if it exists in the image, right? So it doesn't typically give false positives because of how graphs work. But we also found that it identifies closely related or similar trends, things within the kind of error space that might not be exactly right, like 96% of the time. And that's just astounding, right? Because all we did is train it on an idea, a visual concept of an idea. And it's really good. It's probably better than you and I. If we just sit here and flip through images of porosity permeability plots, like we'll probably pick them out visually right about 90% of the time. It's amazing. So, there's a lot of detail in here about the code, right? Like, oh my God, the code. And everybody's high that geologists should all learn to code. And I don't disagree. Learning to code is cool. But this stuff can all be front ended, right? Like we can put the front on things so that all of this digitization process happens from a user interface. Like, we shouldn't have to code as subject matter experts in order to leverage modern technology. And this is like the wrap up of the talk in my soapbox, which is, think about, computers. They were command line only until the mid 80s, right? And what revolutionized things? A graphical user interface. And why did it revolutionize things? Because human beings are visual creatures. We're good at it. And so a lot of our technology should be focused in this image-based visual recognition space, because it's actually what the majority of our work is. We're constantly working at visual recognition tasks. And if you don't believe me, you're doing a visual recognition task right now watching this talk, right? So again, we can just put a front end on this. We can generate points, blah, 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 click through, bing, bam, boom. It's a sweet application of something that's so nascent. It's such a new technology, right? Like the ability to do this didn't exist 3 years ago. Why not? Because the GPU calculations of training models and all of that crap was so time consuming and so costly. You had to have such a powerful machine. Like we can leverage it and do it on our home machines or in the cloud right now with infinite scalability. And so what are the applications? I mean, I don't know, literature searching, finding things, concept identification, prospect identification, data integration. Operators and geologists have millions of images on their hard drive. Like I have like 1.2 million images and I'm just a guy. And you can take this approach with any visual pattern recognition task. Like I dare you to come up with one where it doesn't work. It might be hard, it might be challenging, training might be slow, but you can get there. If you can teach a car to drive itself, you can teach a computer to augment your geologic vision capabilities. Absolutely. So that's what I have for my talk tonight. Thanks.
Appreciate that. Appreciate that, David. Thank you so much for that. So I thought I would go ahead and open up the floor for questions. You could submit your questions in the Q&A on the bottom or the chat. I actually have a few questions myself. So just to get started, David, how have you, so you talked about like web plot digitizer and applying this to digitizing like old visualized representations of plots, but have you done anything, like have you explored some of like the core, like I work in the core analysis space. So is there anything you've done in the core analysis or the imaging space for like thin sections or cores just yet, or any experience that or any ideas?
Totally. We have done that. You can do it. It's all about what you want to find and how you train the machine to find it. So, for instance, we've done a roundness categorizer, right? So it might look at the roundness of grains as well as the amount of round grains. We've done things like straight up facies recognition. So if you put in a core photo, we block that photo out into, they're facies, right? But like you have to train the model and what it's seeing, and you have to use the right model because the visual texture of rocks might look the same across depositional environments. So like it's really easy to get lithofacies such as bioturbated mudstone or sandy mudstone, but it's more difficult to get depositional environment and facies, right? Like you have to combine multiple things to get that to work. We've also done things like seismic line features. So picking out fold and thrust belt on a series of seismic lines, or picking out a channel and a series of attribute slices out of seismic. Like if it's a visual recognition task, you can train a model to do it.
Okay, cool. I know I've explored that kind of stuff personally, so I was just curious what you're doing. Nice string, by the way. So we got a question also just submitted here. Are you able to test different algorithms? Are there different algorithms that work better with seismic data versus plot data?
Yeah, that's a great question. Okay, so first, let's address a couple of things. So what we are principally doing right now is called transfer learning. So we take a trained model, a neural network model, usually of some flavor, that's been trained on a series of images, usually not geologic at all. And we might retrain a new layer based with new images. And most of the time that works okay, because the model knows how to recognize features, right? This is ambiguous, but when you get to very specific different things, you might want to start with a different base model for that transfer learning, or you might want to train a neural network from the ground up. It depends on things like image resolution, contrast in the images, the type of features, if they're linear versus curved, there's all kinds of nuance to it. And actually experimentation is one of the best ways to figure it out, because it's actually pretty fast to try out a bunch of multiple models, but there's no hard and fast rule for like, this model's best at this and this model's best at that. They're all good at different things, but it's not entirely obvious how they'll be good in geoscience, because not very many people have done that. So yes, you should try different models. You should try ground up training of neural networks as well as transfer learning. And it all depends on how much time and energy and effort you have to put into something. So,
that's a good question too for me, to follow up from that I have as well, made me think about it. So I know that when you work with image data, that's probably the closest you can get to big data in oil and gas, because especially if it's 3D. But have you explored? I know there's like different types of machine learning. There's just machine learning as a concept, and there's like deep learning, where you're like getting to these really like large networks that have all kinds of little modules and processes in them, which are really designed for like really large or rich data sets. Have you explored with the deep learning side of anything, out of curiosity?
I haven't seen that there's much to be gained there for the computational and time cost. So it's not to say it doesn't matter. Again, it's all application specific. It depends on how complicated your tasks are. So like I would say this: make your machine learning model do the simplest thing you can make it do. Don't try to write one enormous model that does everything in the whole world of geoscience. That's like destined to fail. But if you can pick a task and you can be specific about that task, it's much simpler to train and execute. So yes, deep learning is a viable path. Is it necessary? Probably not. Is it sexy and do people spend a ton of time on it? Yes, it is. Like, I don't know, what do you want? Like, we're not actually creating the brain, right? Like we're creating a task doer. It's something that helps the geologist have thinking time rather than task time.
Got it. Got a few more questions also submitted. Thank you for that answer, David. So this one is kind of a nice little question. Can you recommend any public domain neural network software? I think this opens the door for a lot of recommendations. So to tag on to that question, I mean, what is your developer kit, if you will?
Yeah, the easiest, most approachable way to do this is programming in Python and using TensorFlow or scikit-learn. Those are probably the two most accessible packages. Tons of people write articles about them every week. There's a new example that you can turn into a geology example, and all you have to do is copy and paste code. You don't have to be that technical, because the good thing is you're a technical geologist, right? So you can look at the results and see if they work or not. And it doesn't really matter why they work for the experimenter, right? It matters, does it do the task or does it not? And if it doesn't, then you need to try a different approach. And then you might dig into the nuance of why a model works or doesn't work, or what a model does. So there are a lot of different things you can try, but those are cheap and easy. I don't know, Doug, are you already a programmer? Do you already program? Maybe we can get a yes or a no in the chat there.
Yeah.
In the meantime, let's address the next question.
Like. Yeah, absolutely. We'll see if Doug responds in the chat. And The other question,
yes, he
while
does.
we wait for that one from Patrick, and he said yes. I'll let you finish then, and maybe you had something to follow up with on that.
Yeah. So then I assume you probably program in Python. So I would get cranking with scikit-learn and with TensorFlow. You can use Keras, right? That's like the translation layer between Python and TensorFlow. And that stuff's cheap, easy, free. You don't have to do anything. You can most likely run it on your own computer. Start with small data sets and figure out what the threshold is. How much do I actually need in order to do the task? Like, it might not be as much training information as you expect.
Yeah.
So
here's a great question.
Oh, C++. Damn it, Doug. Well, you can pick up Python just real easy then, because C++ is way harder.
Oh yeah. C++ is like way harder.
Way harder. It's gonna be like going back to kindergarten for you, Doug. Don't worry about it.
Yeah, you'll blaze through Python. There's probably and I'll throw on some things. I've as a geologist who did some data science myself, I would say that there's a lot of free courses out there. You know, you can do things like Coursera has some really good Python programming courses if you want to get the ball rolling, or even like Udemy or Udacity. There's like tons of them. They're all out there. Just read the reviews. I think you can take a course like that for relatively cheap, and you can probably get off to, get rolling pretty quickly. Totally. Especially if you had experience in C++. I mean, that's way more challenging, way more difficult. Really good question from Patrick here, and I like this question a lot because it really opens up a lot of I don't know, rabbit holes, if you will. But it kind of focuses on a part of the talk that you already were discussing. In the case of using interpreter-specific interpretations to train your models, is there a concern or way to account for bias?
Yes. Okay. Yes, every set of training data will likely include some bias. It's the trainer's job, and especially if you're a domain expert in geoscience, it's your job to hopefully know what your biases are and understand how to avoid that. So like in an image-based model, one way to avoid bias is to have an even number, or not even, but the same number of images in each training category, right? So if I have 5 trends that I'm trying to identify, I might want 500 images from each trend. And that will help eliminate bias that's created by only having a couple in a category. I might also address it by, in my case, what I've demonstrated here, we only have images that are clean, right? Like they don't have any distortion or issues or noise on them. But if we're looking at old images, we might want to do that. If we're looking at images that have grid lines in them, we might want to include a group with grids and a group without. Like, again, there's almost no way to account for every possibility in a model you train. But if you train a small enough model, it can be retrained for different things. So like, we now have one that does noisy images. We have one that does skewed images. We have one that does, images with grid lines on it. We have one that does non-standard plot dimensions, right? Because not every plot has the same 0.1 to 10,000 and 0% to 25% or whatever it is. So like, depending on what you're doing, you have to account for a very big world of possibility. Okay. The other thing about bias is that you probably want to train from a diversity of environments if you're making too big of a thing, right? So look, if I'm only interested in shelf sandstones, like that might be what I'm exploring for in the Rockies. It doesn't matter if my model's biased to shelf sandstones because that's what I'm working in. Like, but if I want a model that I'm going to apply everywhere, I have to contain like every type of sandstone. And so it's really fit for purpose. But again, my advice is make the smallest functional model, make it fit the littlest use case, because then you're less likely to introduce bias through not having a balanced data set. And that's not the perfect solution, but it's one of many. Right.
Good. And having built some models myself, I would also even add on like you could even account for bias with the way you split the data. So there's different types of splits. And you talked about it in your part with your training data and validation data, which is meant to capture that bias, whether your model is overfit or not. And you can either do like, oh, I'm going to take 70% of the data and I'm going to train on it, or 30% I'm going to train on it, and the remainder I'm going to validate with, as in it's not going to be in my model, but I'm going to test the answer versus the prediction on those. And there's different techniques around this, just the whole sampling side, like k-folds and things like that, that you can use to address bias in your model. So that's a whole science in and of itself, really.
It is, and it's something that, again, make a smart model and it's less impactful. And by smart, I mean it's like it's measurable, it's trainable, it's actionable, it's quantifiable, it's got KPIs. Not something so nebulous. And in doing that, it will make you less, I don't want to say less error prone, but it'll make what you're doing like less critical. So, I get asked every time I talk about this stuff, like, well, can it pick a well location? Sure, it can. Do you want it to? Absolutely not. Because you cannot account for all the variables simultaneously to pick a location. What you can do is balance the errors and issues in each aspect of picking a well location and then merge those things together. So you don't want to fail on your entire model by making too generalist of a piece that makes the whole thing fall down. And there are a lot of AI and ML companies that do that, right? They want a silver bullet. And it's mostly because, that's what it takes to make a commercial product for a lot of people, is it has to do everything for everyone rather than the small task that somebody really needs. So that's, I guess, the end of my take on that.
Awesome. Well, we're kind of running out of time here, and I wanted to just go ahead and thank you, David, for taking the time to participate. I think we have many people in the audience thanking you as well. So thank you for that, for participating and sharing with us your kind of experience and journey applying data science and visualization techniques to an industry very dear to all of us. So as if y'all don't see that, David put his email in the chat. So feel free to follow up if you have any additional questions. And also, just to tag on what Patrick said, if you are looking to get into this and you want to train, Kaggle is another great resource, just kaggle.com for data sets. And the final thing I want to mention is just to once again thank our sponsors at both Sizeware and EasyCopy. Without their participation, events like this would be a lot harder to host. So turns out Zoom isn't free. So thank y'all so much for sponsoring, and thank you for all the attendees to come out tonight. David, thank you so much, man. I appreciate it. And with that, I was going to go ahead and close up. Do you have any last comments?
No, just thanks everybody for their attention. I see we didn't even drop participants, which is usually a foregone conclusion in a data science talk. So I appreciate everyone hanging in there, and connect with me on LinkedIn, hit me an email, and let's keep talking about this stuff, because I think it's a really exciting future for all of geoscience. Whether you code or not, it's going to change the way you do work, and I think it's going to be for the better. So
couldn't agree more, David. Okay, awesome. Well, guys, I wish everyone a great evening, and we will just stay tuned for future events and announcements from HGS.
All right. Thank you very much, everyone. Bye.
So long.